Hi everyone, and welcome to the final instructional video for the academic year in AP Calc. This one is going to be dealing with L'Hopital's rule. The objectives for this one are recognize limits that produce indeterminate forms, and number 2, apply L'Hopital's rule to evaluate a limit. Now, earlier this year, we did talk about indeterminate forms in terms of when we looked at limits, and it really came about when we were finding the derivative, and we came about with the definition of a derivative. Really, what you have, indeterminate forms are going to be limits that come out to be 0 over 0 or infinity over infinity. Now, the infinity over infinity does include the different ways of coming up with that. Could be like you could have infinity over infinity, or you could have negative infinity over infinity. That's indeterminate, as well as infinity over negative infinity, or negative infinity over negative infinity. Those would all be indeterminate forms of that we would consider this particular form here. There are 4 other indeterminate forms that can be dealt with. 0 times infinity, 1 to the infinity power, 0 to the 0 power, and infinity minus infinity. Our main focus in terms of, for our purposes with this, is going to be in these first 2 up here. These other ones, what you do is you are able to do some modification on these to change them into one of the forms up above. The next thing I'd like you to do is I'd like you to recall from section 2.1, way back in September, on page 101, we had a definition of the derivative. One form of it was that f prime of c equals the limit as x approaches c of f of x minus f of c over x minus c. Now we're going to use this version of that definition of the derivative to evaluate limits that come out to be one of those first 2 indeterminate forms, either the 0 over 0 or either positive or negative infinity over a positive or negative infinity. So in this case, we're going to let f of x and g of x be 2 continuous and differentiable functions on an interval that contains c, such that f of c and g of c both equal 0. So this is going to be an important part here. And that g prime of x does not equal 0 except possibly at x equals c. We want to have that in there just to make sure that we have something that is defined here. So if I let some function h of x equal f of x over g of x, it's very obvious from there that, based on our definition, that the limit as x approaches c of h of x would come out to be 0 over 0, one of our indeterminate forms. So what we're going to do on this is we're going to modify h of x. And so what happens on this, we're going to let h of x equal f of x minus f of c over g of x minus g of c. Now I can do that on this case because the way we've defined f and g up here is that f of c and g of c are both 0. So in essence, this fraction right here is basically the exact same thing there. We've just added 0 to the numerator, or subtracted 0 from the numerator and denominator. Now I can also go through on this, and I can multiply or divide top and bottom, the numerator and denominator, by the same thing. So I'm going to say h of x is also equal to f of x minus f of c over x minus c. And it's equal to over g of x minus g of c all over x minus c. What you should recognize on this is that that is still an equivalent of function for h of x, because I have just gone through and I've literally multiplied the numerator and the denominator by 1 over x minus c. And so with that, when I take the limit as x approaches c of h of x, that's going to be the limit as x approaches c of f of x minus f of c over x minus c all over g of x minus g of c over x minus c. And what we saw from the definition of the derivative that we saw in the previous slide is that that numerator, this right up here, is just f prime of c. And that is going to be g prime of c. So I can say that this is just equal to f prime of c over g prime of c. Or I could say that is equal to the limit as x approaches c of f prime of x over g prime of x. Take a minute right now, stop, pause the video, make sure you're comfortable with everything I did, especially that you're comfortable with the fact that if h of x equals this, that can be transformed into this, and then when we take the limit, we can get that result. Now let's go and formally state L'Hopital's rule. We're going to let f and g be functions that are differentiable on that open interval from a to b, and that interval does contain x equals c. And it's except possibly at c itself, so it might not be differentiable there. If the limit of f of x over g of x as x approaches c produces the indeterminate form 0 over 0, then I know that the limit as x approaches c of f of x over g of x is equal to the limit as x approaches c of f prime of x over g prime of x. Now, this L'Hopital's rule does apply to these other four indeterminate forms, the ones involving either the positive or negative infinity, because there is some modification that can take place to take something that is in this form and put it into that form. Please recognize that this particular derivative, this form of L'Hopital's rule, does not in any way change the quotient rule that we have for finding the derivative of a function that happens to be a quotient. So now let's take a look at some examples where we can apply L'Hopital's rule. In this first example, we have the limit as x approaches negative 4 of 2x squared plus 13x plus 20 over x plus 4. Now, the very first thing you must do before applying L'Hopital's rule is verify that you do have an indeterminate form. So in this case, in that numerator, when I plug in negative 4, if I do a direct substitution, I'm going to get 2 times 16 plus 13 times negative 4 plus 20 over negative 4 plus 4. And if I do those calculations, 2 times 16 is 32. 13 times negative 4 is negative 52. And then adding the 20, well, 32 plus 20 is positive 52, minus 52. I get 0 in the numerator, and I get 0 in the denominator. So what I can say with that is that by L'Hopital's rule now, that this limit that we're trying to find, the limit as x approaches negative 4 of 2x squared plus 13x plus 20 over x plus 4 is equal to the limit as x approaches 4, or negative 4, sorry, negative 4, of the derivative of the top, which is going to be 4x plus 13 over derivative of the bottom, which is 1. And when I plug in the negative 4 in that, I am going to get negative 16 plus 13 over 1, which comes out to be negative 3. So the limit of this, as x approaches negative 4, of 2x squared plus 13x plus 20 over x plus 4 is equal to negative 3. Let's take a look at another one here where we're going to involve different types of functions. In this case, we're going to take the limit as x approaches 1 of the natural log of x over sine of pi x. Well, again, in this one here, when I plug 1 in, if I do a direct substitution, that's going to be the natural log of 1 over the sine of pi, which the natural log of 1 is 0, sine of pi is 0, so it is 0 over 0. I've now verified that I can do L'Hopital's rule. So I can say now that this limit as x approaches 1 of the natural log of x over the sine of pi x is going to equal the limit as x approaches 1 of the derivative of natural log, which is 1 over x, over the derivative of sine x, which is sine of pi x, which is going to be pi times cosine pi x. So if I plug 1 in there, that's going to be 1 over 1, which is 1, and pi times the cosine of pi, where the cosine of pi comes out to be negative 1. So this results in a negative 1 over pi. So the limit as x approaches 1 of natural log of x over sine pi x comes out to be negative 1 over pi. It's important that these limits can also involve infinity in some way. What I want you to remember on this is that if there was one thing to recall is if I take the limit as x approaches 0 of 1 over x, that is going to be infinity or negative infinity. And the limit as x approaches infinity of 1 over x does come up to be 0. And a lot of times what I tell people is, the way you can think of it is that if you do a direct substitution and you get a constant over infinity, you can think of that as 0. Or if you get a constant positive or negative number other than 0 over 0, you can think of that as infinity. So if I do a direct substitution like in this one, I would have 1 over 0. I will automatically think of that as infinity. So in this case, our next one, we have the limit as x approaches infinity now of x squared over the square root of x squared plus 1. Well, in this particular problem, that one, if I plug in, do a direct substitution in there, I'm going to get take infinity, put infinity in for x, I'm going to get an infinity squared is infinity, over the square root of something very big, and the square root of infinity is also infinity as well. And so I have the indeterminate form. And so I can now go through and say, well, that's going to be equal to the limit as x approaches infinity, where I can apply L'Hopital's rule. The derivative of x squared is 2x over, now the bottom. Remember, that is, the square root is to the 1/2 power. So I can think of that as 1/2 times x squared plus 1 to the negative 1/2 times the derivative of the inside function, which is 2x. Well, simplifying that, the two x's would drop off. They would cancel each other out. And remembering that that's this x squared plus 1 to the negative 1/2, that is going to be the same as 1 over, that denominator is just going to be 1 over 2 times that square root. So that is just going to simplify as the limit as x approaches infinity of the 2 times the square root of x squared plus 1. So in that case, this is just going to be infinity. Let's look at another one here. This time we're going to take the limit as x approaches infinity of the natural log of x, that quantity squared, the natural log squared, over x cubed. Well, again, by direct substitution, natural log of infinity does go to infinity, so it's going to be infinity over infinity. So it is something we can use L'Hopital's rule for. So that we know is going to equal, we can apply L'Hopital's rule, that's going to equal the limit as x approaches infinity. The derivative of the top is going to be 2 times the natural log of x times the derivative of natural log, which is 1 over x, all over the derivative of the denominator is going to be 3x squared. One thing I want to take a pause for a second before we move on. Please notice that this squared right there, I can't pull that out in front of the natural log because that's a squaring of the natural log. If that had just been a squaring of the x, then I could pull it out. But because of where it's located, I can't just pull it out. So to get this derivative here, I did have to apply the chain rule. Start out with the squaring, this 2 moved out in front, times the natural log of x to the first, which is just ln x. And now so that's how I got there. Now I'm going to simplify that, and that's going to be equal to the limit as x approaches infinity When I simplify that, because that's this the 1 over x could actually be brought into the bottom, that is going to be 2 ln x over 3x cubed. And again, now when I do this, when I do that direct substitution, I'm going to get infinity over infinity. Well, that's an indeterminate form. So what does that mean? It means that we can do this again. So I know that that limit right here is going to equal, by L'Hopital's rule, it's going to equal the limit as x approaches infinity of the derivative of the top, which is going to be 2 over x, over 9 over x squared, which I can simplify that. That's going to be the limit as x approaches infinity of 2 over 9x cubed. And as x goes to infinity there, that is going to result in a 2 over infinity, which we can think of as 0. So therefore, the limit as x approaches infinity of the natural log of x squared over x cubed does come out to equal 0. Now, one thing that happens when people are working with L'Hopital's rule that you have to be careful of is people start applying it at all times. I know when I was in your shoes, once I learned L'Hopital's rule, I started trying to apply it all the time, and it only works when you have that indeterminate form, the infinity over infinity or the 0 over 0. So it's very important that first step must be always to go and just do a direct substitution and check to see if you can actually apply it. So in this case, on this first one, these are ones where we can't apply it. When I do the direct substitution in this first one, as I put 0 in there, my numerator is going to be 0, the denominator is going to be -1. That is not an indeterminate form. That is 0. And so the limit of that as x approaches 0 of that function is 0. In the next one, limit as x approaches 1 of cosine pi x over the natural log of x. That one is, when I plug in 1, I get the cosine of pi over the natural log of 1, which cosine of pi is -1 over the natural log of 1 is 0. So in that case, that is not an indeterminate form. That is a constant over 0. So we can sit there and say that that limit actually does approach positive or negative infinity. And the next one is probably the one that where people will make the most mistakes on in terms of applying L'Hopital's rule. And in this one, what you have to remember on this, the limit is they see the limit as x goes to infinity, and they look at the bottom, and they say, oh, that goes off to infinity, and they think about sine x, and people start automatically assuming that a function goes off to infinity or negative infinity as x approaches that, or it's going to approach a number. Well, you have to remember, sine of x oscillates between 1 and -1. It does not, so it is just going to always be a value between 1 and -1. It's not going off to infinity. It's not going off to 0. It's not going to be necessarily 0. So this one really does not have, sine of x really does not have a limit. And so on that one, because of that, we can't really say you don't have a limit, but it is something, it's going to be some value here between -1 and 1. And that's going to be infinity. And because we're taking some value between -1 and 1 over infinity, that limit does come out to be 0. Okay, so it's not going to be, we're not applying L'Hopital's rule to that particular problem, even though a lot of people will automatically, they'll start applying it there. Now, the other thing I want you to remember on this one, I am showing you L'Hopital's rule at this point, but at this point in time, this particular rule is not tested on the AP exam, but as with other topics, it is something that you can use. And so there will be some problems. There could be some problems where you're asked to find a limit that would, if you do the substitution, you do get something that would be an indeterminate form. They're not expecting you to use L'Hopital's rule, but it would be an acceptable way to actually do it. What they would actually be expecting you to do is recognize really one of the forms of the definition of the derivative. Anyway, with that, this does conclude the video on L'Hopital's rule and the indeterminate forms. Remember, what we're going to be focused on is just the infinity over infinity or 0 over 0 indeterminate forms. If you would like to see how you deal with some of the other forms, I can sit down and do that with you. But at this point in time, this does conclude our the topics that we will cover before the AP exam, and we will, from this point forward, be looking at preparing for the AP exam. So with that, I thank you, and I will see you in the next class.